Welcome to part 3. Now, this part will be the final part for the reactions. Okay, I think we have from AK to around AV. So we'll just do these and the list will be over. If you have any queries, please feel free to ask. Now, AK reaction with nitrous acid. Now, nitrous acid, we normally use the diazonium salt. But in reality, this happens Okay, in reality, this happens with all um, with all of the groups. Okay, so as long as you have an NH2, even amides will be able to undergo nitrous acid. Okay, will be able to react with nitrous acid. So ethylamine. So this was AK. To give in the presence of NaNO2, you always prepare this in C2 and HCl, CH3, CH2, and 2 plus Cl minus less than 5 degrees Celsius. Phenylamine, same thing. So phenylamine is going to be so much more stable because of resonance forms. And this is exactly why we normally just use phenylamine, okay? But they will all work, okay? In fact, they will do the same reaction. Then Al was the coupling reaction. So we have the diazonium salt with phenol, and this will always react opposite of the phenol. It's a 2,4 directing reaction, phenol. But since it's a bulky group, it goes opposite. Of course, if there is no available room opposite the phenol, then it will go into position 2. Okay, so there were to be a methyl group here to go to position 2. But the reality is, you try to go opposite to avoid steric hindrance. AM, this is about amino acid. So you have the same amino acid. Actually, this is not an amino acid, so I'll explain the difference. If it were to be an amino acid, there would have had to be a functional group here. Actually, no, this is glycine. But this is not, so it's an amino acid, but it is not optically active. The only amino acid that is not optically active. Okay, so we have either with plus HCl or plus NaOH. And NaOH, you'll actually have the reaction on the carboxylic acid. HCl, you'll have the reaction on the amine. Again, this is a normal acid-base reaction. Okay, so it's a normal acid-base reaction. Just because there are two functional groups doesn't mean anything else will change. Okay, now chemical reactions. You have the reaction of glycine with ethanol in the presence of HCl gas. Now, this, as far as I'm concerned, okay, as far as I'm concerned, is the same reaction that we've just done for um, glycine with HCl. Let me confirm for 1 second. But with glycine, if you actually have transition metals, you can end up um, forming a ligand. Okay, but for the first reaction that you have here, so AN is the same as this one. So AN is the same as that one, AN1. Then a reaction between two molecules of glycine. This is the formation of a peptide bond. And it's just two molecules. So do not complicate life by trying to have either more or trying to write the brackets. It's just two molecules. You just form a peptide bond and you lose water. Okay? And now, as I told you before, anything can react with NaNO2 and water, and therefore, if anything can react with NaNO2 and water, amino acids can do it as well. It's gonna be much less stable, but it's okay. Okay? It's the NH2 group. You just need to know that it is the NH2 group. AO, formation of the nitrile. So you have three reactions here. You have bromoethane plus Cn minus. You have propanone plus Cn minus. And you have the diazonium salt plus CuCN. The first one is a simple substitution. This is used anytime you need to increase the carbon bond by 1. This is a nucleophilic addition. This is important whenever you need to both increase the carbon chain by 1, but you also need to increase the functional group. And this is used when you need to add a carbon to benzene. Remember, you can add using the alkyl or alkylation or acylation method, but this offers more flexibility. Okay, if you want to form an amine, if you want to form a carboxylic acid, you might want to tell me about the carboxylic acid. You can still add it using methyl and then potassium permanganate. Fine, but maybe you have other groups that will interact. Okay, so the nitrile can always be used to add a carbon chain. Then you have hydrolysis of the hydrolysis of the nitrile, either acidic conditions or under basic conditions. Now, MetSec, whenever you have schematics, they always give the basic one because they always give the salt. And then you add H plus to get to the acid. This reaction will also work directly using acid. Now, some of you told me this week, but shouldn't I use the acid because the reaction will be one step shorter? Yes, but if you have a schematic and you realize you have a nitrile, normally 99% of the cases, if it's 99.9, they go with base, then acid. Okay, the reaction is better. Sometimes 2 steps are better than 1 if you're gonna get a higher yield, and this reaction just runs smoother and sweeter. This is also allowed. I do not see in a scenario where they will reduce marks for writing two reactions like this instead of that one because of it wasn't the shortest route. And don't believe that that actually matters. Okay, the important thing is that you get it correct. AQ, rejoice, we're on the last page now. The reduction of nitriles. So AQ2 you do not have. Okay, so you have the C. Apologies for giving that. This is a reduction. Nitriles can be reduced to amines, both with lithium aluminum hydride or using nickel and hydrogen. So both of these will actually give the this same product, okay? But LiH4 is nucleophilic and NiH2 would reduce any pi bond. These can be prepared, okay, from, so this is AR. These can be prepared from amides through what we call a dehydration reaction. Okay, so this you are removing water from the molecule. And now we just have the reactions of benzene. So we are very nearing the end now. So benzene, you have four reactions. Okay, I think overall I did all of the reactions, but be aware that certain things might be more, you might have a few more of these. Okay, so let's start with HNO3, H2SO4, 50 degrees Celsius. This is nitration. The first step, if you want to draw the mechanism, and eventually we'll be doing this again, you'll have to react the HNO with H2SO4 to form an O2 plus. Okay, I hope you know the drill by now. This is Br2 with FeBr3. It will also work with AlCl3. That was my mistake when I was writing it. But the catalyst is Br. It's Br, FeBr3, so that the catalyst will be the same. AlCl3 will work, but it will not remain the same. Chloromethane, so the catalyst, if you're using bromine, it should have Br. If you're using chlorine, it should have Cl. Chloromethane with AlCl3. This is the addition of the chloro group, of the methyl group, and propanoyl chloride will introduce the acyl group. With these you have sulfonation, and you also have addition of hydrogen and addition of chlorine. But again, I think this exercise was a very good exercise to get you to go through the motion, okay? To push you to actually work a little bit of everything. After this, you had toluene. The first reaction, okay, it was similar, HNO2, H2SO4. So here you're gonna have the nitro group. The nitro group will add onto two positions, either 4 or 2. I'm gonna put it on 4. To be honest, ratio-wise, the 2 will have a little bit more. Actually, let me write both. The 2 will have a little bit more, simply because there are two positions where the 2 can be, because remember, this position and this position are the same. But it's not exactly the 2 is to 1 ratio with the positions, because again, this is a little bit less sterically hindered. Then, methyl benzene with chlorine in presence of UV light, Cl2 UV. This means it will react with the CH3, so which CH2Cl, but you can also have Cl2 with Fe or AlCl3, and this will add the chloro functionality to the benzene ring. Another reaction is with KMnO4. KMnO4 isn't just for methyl benzene. KMnO4 will work and reflux every time you have an alkyl group, and it will break it down to the benzoic acid. So this is always, always, always the same. Okay? You also remember have, and I'm gonna write it here. It wasn't one of the questions. With CrO2Cl2, which will give partial oxidation to the aldehyde, to benzaldehyde. AU, nitrobenzene with HNO3 and H2SO4. So this, remember, for these normally you're gonna have the same reactions. They are all the same as benzene. The only difference here, not the problem, difference is that it will be in position number 2. Okay, and you have the reduction. Then and HCl to form phenylamine. The last set, AV, it's with phenol with sodium, you form the salt, similar to an alcohol here, and hydrogen. With NaOH, this will not happen with alcohols, but it will happen with phenol. With NaOH, it will still react to form, at this point, H2O. It's acidic enough to do this reaction. Bromine water, without actually having a catalyst, you will get all the brominations. This will form the tribromine, and it will happen without the need of a catalyst. It's because the phenyl group, the OH, is especially activating. With ethanol chloride, this is the esterification. Remember, phenol doesn't form esters with carboxylic acids. It's not activated enough. It's not reactive enough. Therefore, you need to use something a little bit stronger. And with FeCl3, this is a test. This gives a purple coloration. If with FeCl3 you get a reddish brown coloration, that means you have a carboxylate. Now there was another one. There was the phenol with dilute nitric acid. This should be protonation. Now, protonation is when you add a proton onto the oxygen, and alcohols can definitely do this. Also, because phenol is highly activating, it might not need the H2SO4 to form the NO2 plus catalyst. As far as I'm concerned, again, this you do not have in your syllabus. So again, it was my bad when I was writing the questions. Okay, but I hope this was plenty useful for you. And if you need anything, just